Okay, in the last couple of chapters, we've essentially spent all of our time trying to find every possible way to integrate any function we can. And when we couldn't integrate certain functions, we then used tricks like the trapezoidal rule and Simpson's rule to approximate the value of the integral. And we established at the beginning of the semester, the ultimate goal of this class is to be able to integrate everything. And at this point, there are still a lot of things we can't integrate, but we've kind of exhausted all of the algebraic tricks that we can come up with. So we're gonna have to do a lot more work to come up with ways to integrate different types of functions. But we're actually gonna kind of go away from that for right now, and we wanna kind of reinforce all the integration type tricks that we know and some of the ways in which we can use them. And the standard way to use them is actually a way that you should have already seen in Calc 1, meaning if I told you A of t is equal to 6, where A of t, or yeah, we'll say A of t, where A of t is acceleration, can you find the velocity? Well, yeah, you would have done that in Calc 1, and you would say, oh, if that's the acceleration, to find the velocity, velocity is the first derivative of the position, acceleration is the second derivative, so I just have to go backwards. So I anti-differentiate. And then I would get that the velocity is just equal to 6t plus c. And then normally you would be told something like v sub 0 is equal to 5. So then I could plug in, when this is 0, I need to get 5, which tells me that c is equal to 5. So then I say v of t equals 6t plus 5. And then for the sake of argument, you would then go with, if I have the velocity, what is the position? And you would say, oh, I take the velocity, I anti-differentiate to get the position. And you would get h of t is equal to, let's see, 6t squared over 2 plus 5t plus c. And then normally you'd be given some condition for position. Say h of 0 equals 2, which if I plug it in would then imply that c equals 2, and I would ultimately arrive at my function h of t, I can simplify this, is 3t squared plus 5t plus 2. And we have this idea that I start, say here, and then I learn about derivatives. Derivative of position is velocity, derivative of velocity is acceleration. And then once you know how derivatives work, you say, can I do things in reverse? Can I start at the end and go backwards to get velocity, and then go backwards again to get position? And yes, that's where our ideas of anti-derivatives come from. So now we want to kind of take that idea and expand on it, because while we definitely use it for simple problems like this, there are a lot more complex problems we can have where we need to anti-differentiate, and we want to kind of look at all of those. Meaning, well, if I have this, I could write dy dx equals x squared. And we understand this is derivative notation, Leibniz notation. If you prefer, we can also write this as y prime equals x squared. And the goal is to ultimately find y, the original function that would result in that derivative. And in this case, it's really, really clear, well, if I anti-differentiate, y should clearly be x cubed over 3 plus c. Because if I take the derivative power rule, I bring down the 3, it cancels, and I'll be left with x squared, and the c just goes away. This is a class of problem called a differential equation. And in this chapter, we're essentially going to be solving different types of differential equations out. I will point out, there's a lot of differential equations out there. As I'm sure a lot of you are aware, there's a whole class called differential equations that we offer. And that in and of itself is really just the first differential equations class you can take. There's a lot more you can do with differential equations. So this is kind of a really broad topic. For the purposes of this chapter, we're really just going to be looking at a few different classes of differential equations and the different algebraic tricks that we can use to solve them. And I will point out, before we do anything else, these differential equations can be very, 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 very tricky, or they can actually be really straightforward, entirely based on how you look at them. Meaning, for the purposes of the ones we're doing in this class, we will only be looking at differential equations that we already have algebraic tricks to solve. Our goal is to learn the algebraic tricks to solve them. In the same way that we know how to take the derivative using a product rule or a quotient rule. And ultimately, you look at the problem and say, this is a product, apply the product rule. This is a quotient, apply the quotient rule. It'll kind of be the same idea here. We'll have different differential equations. Our goal will be to classify them. Oh, this is a, you name it. And then once you know what type of differential equation it is, that will dictate the rule, the trick you use to solve it, just like power rule, product rule, quotient rule dictates how you take a derivative or an integral, you name it. So the terminology here is really important, but as long as you keep that straight in your head, literally being able to name the problem, oh, this is a separable differential equation. Don't worry about what that means. We'll get to it soon. Immediately tells you how to solve it, and then you're done. So you don't really have to make stuff up to solve these. It's pretty much just classify them, that tells you the trick, and you're done and good to go. The algebra is not all that challenging. It does get challenging later on, but for right now, for what we'll be doing, it won't. So keep that in mind. But we're not really going to solve a lot right now. Right now, we more want to do what we did with derivatives and with integrals. Maybe start by getting an idea of what these differential equations are and what they mean. And then, if I can't necessarily solve them because I don't have any tricks yet, see if I can find ways to approximate solutions. And then once I have an idea of how to approximate a solution, maybe I can use that to then generate ways to get actual solutions. Again, a similar approach to what we did with our derivatives and our integrals. So, ones like what we had just right there are really, really straightforward. So we actually don't even need any tricks, even if I didn't tell you it was a differential equation, much like with the acceleration and velocity and position, you could just look at the problem and figure out how to solve it. Our goal is to work with ones that you can't just look at and solve without learning tricks. As an example, suppose I have y double prime minus y prime minus 6y equals 0. And keep in mind here, y is a function, y prime is the derivative of y double prime is the second derivative of y. And the goal of this and of all differential equations is to find y, the function that you can plug in and solve that differential equation with. Sometimes we will find y implicitly, other times we will find it explicitly. The ultimate goal is to find an explicit solution, y equals fill in the blank. Sometimes we can't really do that, so we'll just have an implicit solution, but the ultimate goal is, if possible, to find the explicit solution. But before we actually get to tricks that we can use to solve things like this, we need to understand first what solutions look like and how we test them. Meaning, well, right away, right here, there's clearly a trivial solution, y equals 0. If y equals 0, then y prime equals 0, and y double prime equals 0. And if I plug in, I get 0 minus 0 minus 0 equals 0. So that actually works as a solution. But the question is, are there other solutions, other functions y that I can plug in and make that work? And I can actually just randomly test ones. I mean, if I let y equal x squared, is that a solution to that? Well, I just need to find y prime, which is 2x, and y double prime, which is 2, and then plug them in. If I plug in, I get y double prime, which is 2, minus y prime, which is 2x, minus 6 times x squared is equal to 0. And just so we are clear, I do not need to try to solve this quadratic or do anything like that. If this does not equal 0 immediately, then this is not a solution, because that's what I'm looking for. Something that makes the left 0, because the right is equal to 0. So then right away I can say, no, that's clearly not a solution. And for right now, essentially, say for your homework and all that, you're really just going to be plugging in different values and seeing if you get a solution. And just so we are clear, the understanding algebraically how to do that, to take a function, take its derivatives, plug them all in, solve it all out, and say, yes, this is the solution, no, it's not, is an algebraic skill we want to have, so you will be doing that. So just make sure, I don't want to spend a lot of time on the video doing a lot of needless algebra that you know how to do, but understand you will be doing things like this, and it is important. Maybe for this, how about, I don't know, that's a polynomial, that's 0. Go with an exponential. E to the 3x. Is that a solution? Well, let's see, take the derivative. The derivative of e to the 3x. Rewrite the exponential, take the derivative of 3 to the x, which is 3. I need y double prime. Rewrite the exponential, take the derivative of 3x, which is 3, times the 3 on the bottom. I get 9 e to the 3x. Plug all of those in. I get y double prime, which is 9 e to the 3x, minus y prime, which is 3 e to the 3x, minus 6 times y, which is e to the 3x. Is that equal to 0? 9 e to the 3x minus 3 e to the 3x is 6 e to the 3x. 6 e to the 3x minus 6 e to the 3x is 0. I get 0 equals 0. And apparently, y equals 0 is a solution. Y equals x squared is not a solution. Y equals e to the 3x is also a solution. And that's kind of the goal here. Looking at different types of differential equations, what solutions are there? When y is equal to 0, we call this the trivial solution. And while it will not always work, clearly in a lot of situations it will. So we just call that the trivial solution, and our goal will be to find non-trivial solutions. When is it that polynomial things will work? When is it that exponential things will work? Is there some type of trick that tells you, oh yeah, if I look at that, I should get a polynomial? Well, I guess in this case, no. I should get an exponential. In this case, yes. And with practice, there's different things you kind of recognize. One thing that I actually want you to explore a little bit for your homework that we've actually kind of sort of seen here, but we'll simplify it a little. Suppose I have y prime equals 6y. If I want to solve that, there's different ways to go. But one of them is to say, well, okay, I need a function that if I take the function and take its derivative, the derivative is the exact same as the original function multiplied by 6. 0 will clearly work again. If I plug in 0 there, y prime is 0, and that trivial thing will work. If I use a polynomial, when I take the derivative of a polynomial, the power goes down, so y changes, which means y and y prime are different. So that can't work for something that looks like this. What type of function, when you take its derivative, stays the same, up to maybe some constant multiple? Well, right here. If y is an exponential, The first thing you learn when taking the derivatives of exponentials is rewrite the exponential. You just end up with a constant out in front if your power has a coefficient of x in it. So right away, looking at this, it would kind of be logical to assume that y is equal to some type of exponential. Maybe we'll say y equals kx. And then all I would really have to do is figure out what that k is. Can it be anything? And do I need to put a constant in front? Or, well, if I use the correct k, will taking the derivative bring that 6 down? Or different things like that. And you're actually going to mess around with that a little bit for homework. So I'm going to actually deliberately leave that here for you to ponder and say, what can I come up with to make this work? If that's y, well then y prime would be like, well, if this was y, if I just left that, y prime would be k e to the kx. And now I have a y prime, I have a y, I can plug them both into that and see if there's a way to figure out what k has to be. Because if I know what k is, well then I know what the power is and then I'm done. So I would encourage you, we're going to actually solve problems like this later in the chapter, in the next section actually. But for right now, just think about it. Mess around with it algebraically and see what comes out. But there's an idea here. Well, if I have a function and its derivative is equal to the original function up to a constant multiple, the only function that has itself as a derivative is the exponential, which means an exponential is a good candidate for a solution here. Function, derivative, second derivative. It seems like the only way this could possibly work is if I use exponentials again, because it's the only thing that occurs over and over. As it turns out, in this case, there are actually a few other things that could happen. We'll deal with them later. But again, there's this idea of looking at it and saying, how could this work? Using my understanding of derivatives, what type of functions could work there or here? That is actually what will lead to the algebraic tricks we'll use to solve these things out. But it comes by really just looking at them and saying, what do I know about pre-calc? What do I know about derivatives? What can that tell me about what I think my solutions should look like? And then going from there. But I will leave you with that as far as those go. For right now, like I said, we really just care about being able to take a differential equation, be given possible solutions like we had here, and then plug them in and say, is it a solution, yes or no? Does it make the equation work, yes or no? And now, before we actually look at finding those solutions, we're going to look at approximating them. And there are different tricks you can use. From a mathematical perspective, there's kind of two ways to go. Suppose I have this. dy dx equals, and here we will actually use one that we know, we just did, x squared. Clearly I know the antiderivative of x squared is x cubed over 3, and then I have to put a plus c on there. But we're just going to use this as an example before we do another one. But there's this idea mathematically, if I didn't know that, how could I approximate that? In Calc 1, we learned that the derivative tells me the slope. And I'm sure in Calc 1, when sketching curves, a lot of times what you do is you take a function like f of x equals x squared, then you take the derivative, f prime of x is 2x, and then you plug it in at different points on your graph. At 0, 2x is 0, so at 0 my graph does that. At 1, 2x gives 2, 2 times 1 is 2, so at 1 my slope is 2, which means it's positive, and this gives me an idea of what the graph of my function looks like. That's a standard trick you use to sketch curves in Calc 1. But there, you're starting with the function and using its derivative and my idea about slope and derivative to get the graph of the function. Here, I'm given the derivative, f prime. Can I use that to approximate what my graph should look like? And then from there say, if I know what the graph looks like, maybe I can figure out what the function has to look like. And yeah, essentially it's this Calc 1 trick done backwards. And again, there are different ways to view this. This is kind of the, I have no idea what my graph looks like, so I'm gonna find all possible solutions and throw them on a graph and then go from there. The alternative approach is to pick a particular graph and find it, we'll see how in a little bit, and do that. And from a math perspective, there's kind of this, you can take the broad approach or you can take the really limited approach, and they each have their own pros and cons. We're gonna start with the broad approach here. I'm looking at the time because I have to go teach a class soon, and I wanna make sure I have time for all of this. But we're gonna do the broad approach now, and then I'll make another video going through the more limited approach. But the idea is, we wanna create what's called a slope field. Again, using our idea of slopes, derivatives, that you did in Calc 1 to sketch a curve, now sketch a whole lot of curves. And what you do is, you can make this as broad as you want. I would point out, for those of you who have used Maple before, if you go into Maple, you can actually generate these in Maple, or you can sketch them out by hand. And I have no problem with you sketching them out in Maple. You cannot for your exams, I'll want you to do them by hand. But for your homework and for practice, if you want to sketch these in Maple, that is completely fine. When you turn in your homework, just include a copy of the printout from Maple so I can see what you did in Maple. That will work fine. But for this, all I do is exactly what I did before when sketching my curve. I look at different values in the XY plane, and I find the value of the slope. And in this case, well, anywhere x is 0, x squared is 0. So at 0, when x is 0, all along the y-axis, my slope is 0. So I'll just do several 0 slopes. When x is 1, I get 1 squared, which is 1. So my slope is 1. So right over here, I'll make slope 1 up to my ability to make all of these parallel. When x is 2, I get 2 squared, which is 4, which is positive going up, but it's bigger than 1, so I make it steeper. So at 2, maybe I'll go like this. Once again, up to my ability, that is not parallel, to make these things look parallel. And then clearly, when x is 3, I get 9. When x is 4, I get 16. And the more right I go, the steeper the slopes will get. So maybe I'll just do one more where these get even steeper. And again, each column of these should be parallel up to my ability to draw that. And then if I go on this side, well, let's see. When I plug in -1, I get -1 squared, which is +1, which means I get the same slope as I did there. At -2, I'll get +4. -2 squared is +4. So it will look like that. And after this, we'll stop with this. I think we have enough points here. But now, using that slope field right there, can I get an idea of what y looks like? Well, sure. If I pick an arbitrary point, I'll pick 0, 0 right here. Sketch the graph starting here. Well, according to this, I should start out flat, and then I should start getting steep, and then I should get steeper and steeper and steeper and go up like that. On this side, as I approach this, my slopes should clearly be really steep. I'm going to miss it because I started too low. My slopes should be really steep, but then as I approach 0, they should flatten out. And it should look like that, which is clearly a cubic. But that makes sense because I know the antiderivative of this is x cubed over 3. So the slope field is giving me the solution that I want up to my ability to draw it, a cubic. But I just arbitrarily picked this point to start. What if I picked this point? Well, I would still start off flat, then start going up, and then get steeper and steeper. On this side, I would go out kind of flat, and then get steeper and steeper. If I started down here, essentially the exact same thing would occur. In Calc 1, when you first learned antiderivatives, you talk about a family of solutions. That's why when you anti-differentiate, say if you anti-differentiated this, you always have that plus c. Because you do not get one solution, you get an infinite number of solutions. Which is what this actually shows us. I now know that my solution should look to it like this, up to my ability to draw it. And it should be cubic. The only thing I don't know is which cubic is the actual solution. So this slope field just gives me a visual representation of all the general solutions. If I wanted to make this an initial value problem like we did with acceleration, velocity, and position, I could say sketch a slope field and then find the curve through the point 1, 1. And for the sake of argument, I'll just say this is the point 1, 1. And then I can just draw the solution curve that goes through the point I care about. And admittedly, for this one, I didn't actually need to draw the slope field. Again, we can all anti-differentiate that and get the solution. We can get the whole family of solutions. If I then wanted to plug in an initial condition, I could find the particular solution I cared about. But this shows me that this trick will work. Using my differential equation to sketch a slope field, to then get solution curves using those slopes, and then even if I wanted to, picking a particular solution can work and give me an idea of what's going on. Give me an idea of what my y looks like, means that I can use this trick for differential equations that I can't solve by hand. So we'll do one more of these. And bear with me as I yet again check. Oh, I have plenty of time, good. So suppose we have dy dx equals x over y. Yeah, and I don't have any real idea what the solution to this looks like. We actually will. We'll solve it out in the next section of your book. But suppose I want to solve that. Well, I can find my slope field. And let's see. Clearly, when y is equal to 0, the slope is undefined, which means all along the x-axis, I'm undefined. I can never cross that because the slope is undefined there. When x is equal to 0, I get 0 again. So all along the x-axis, except along, all along the y-axis, except at 0, 0, I get slope equal to 0. Now I just have to plug in individual points here at 1, 1. If I plug in 1, 1, I get 1 over 1, which is 1. At the point 1, 2, I get 1 over 2, which is a half, which is flatter. At 1, 3, I get 1 over 3, which is a third, which is flatter. And clearly, the further up I go, the flatter these will get. If I go over to 2, 1, I get x is 2, y is 1. That's 2, so this is steeper than here, which is 1. But then at 2, 2, I get 1, which looks like that. And then at 2, 3, I get 2/3, which is flatter. And then again, I kind of get this idea. As I go over here, at 3, 1, I'll get 3, which is even steeper. But as I go up, these values will start to get flatter and flatter and flatter. The bigger y gets, the smaller the fraction gets. By the same token, over here, if I plug in negative 1, 1, then I get x is negative 1, y is 1, I get negative 1. If I plug in negative 1, 2, I get negative a half, which is flatter. And then clearly, this will get mirrored over here, just in the opposite direction. Again, up to my ability to draw these reasonably well. And we kind of get this idea that depending on where I start off steep and then I kind of flatten out a little bit based on where I actually start. And for the purposes of this, and to save time, I'm not going to do slopes down here. Clearly, they would mirror these a lot. Based on the quadrant, it would just dictate whether they were positive or negative, because the xy values are the same. The SIGN sign is the only thing that will change. But then if I wanted to try to sketch a curve, well, let's see, if I pick this point, say right here, as I start going out, I'm a little bit flat, and the higher I go, the flatter I get. And maybe it looks something like that. And if I go on this side, again, I kind of come down and approach this. This should be curvy, not pointed. And maybe it looks something like that. Here, maybe if I start here, I start going up, but as I go up, these ultimately flatten out. And as I go down, I either approach 0 here, and then it looks like I'll essentially repeat on this side, or maybe if I start over here, I just shoot down to where I'm undefined. And I get solutions that kind of look like that. And again, does this tell me the solution to the differential equation? No, I mean, that's just my approximation and my ability to graph there. And frankly, I don't necessarily know what type of function those curves give. And like I said, I deliberately didn't do these down here. But it does give me an approximation of what I think the solution should look like, which is all I'm going for. A guess, an approximation of what's going on here. But then again, if I wanted to find the solution to a particular point, again, say this point that we used right here, there's different ways to do this. One of them is to draw this whole slope field like I did, and then find the curve that goes through that point. But frankly, I didn't actually bother to do anything on the bottom, and it doesn't appear to matter for this point. And to a certain extent, doesn't really matter if I do these slopes up here, if I only care about this particular curve right here. No, really then, for this, I could really pick a starting point and then just use the slopes around that starting point to get an idea of where to go to next. And then once I get that next point, find the slopes around that point, and then find the slopes around that point. And essentially the idea is, like I said, there's kind of this broad way of understanding the differential equation by sketching the slopes everywhere and getting an idea of what the whole family of solution curves looks like, then picking the particular solution you want. The alternative is to say, if this is the solution I want, the solution through that point, then rather than finding all these slopes, I'm going to start by finding the slope here, and then based on what I get at this point, hey, it's going up, then I'm going to find the slope at this point. Hey, it's kind of flatter. Okay, I'll find the slope over here. And in the next video, we're going to go over how to actually do that approach, where instead of picking the whole set of solution curves, I pick one at the beginning and then use that as my guide to get my curve, to get my algebraic solution. Ultimately, we want to be able to do both, to get the broad approach to see what's going on everywhere, and then to kind of get the macro approach to see what's going on through a point. That approach will be more algebraic and less graphical, so we kind of get to see things from both perspectives. We get to see the graphical broad approach, and then we'll look at the algebraic or more micro approach. And then again, once we have both of those approximation ideas down, then we'll start looking at algebraic tricks to actually solve these differential equations out, and then we can compare the solutions we get algebraically with the solution curves and approximations that we saw here.